We're not getting an extension.
I always like to do it the first time. If someone has something happen the first time in a class, and I'm not gonna ask questions about what it is, I'm just gonna say, that's reasonable. You haven't asked for an extension before in this class, I'll give you a day or two.
Can we script Canvas to the point where if it's a no, they instantly just get a rickroll when they try to submit it?
That would be fun.
Compound this and make this
Like, there's gonna be a lot of
progressively
wasted effort on the
worse.
students' end.
Yes.
Yeah.
It would actually have you prioritize whether it's worth that effort to do or not.
So for the oldest gotcha meme in existence.
Yeah. I find that currently I have to make a judgment call about what I've been doing for other people in the class. And that way, if I allow it for one student, then I have to allow it for every student. And so if I,
Gets out of hand quick.
yeah, I need to have some policy about what that is. But I also want that policy to have exceptions in exceptional circumstances.
Because there's no policy currently, just in the syllabus.
Yeah.
Yeah.
Yeah, it's due when it's due, and it's up to me what happens for late work. And usually I'm a pretty big pushover when it comes to, I want to see your best work, whatever it takes to do that. But I have had a couple instances of students try to do that on every assignment, and eventually I have to draw a line and say, you asked for 4 or 5 times out of 8 assignments. Something's going on here.
There's a Moses joke somewhere.
Yeah. All right, so tomorrow's our review session. Today is when the assignment is due. If things have been really tough, I know that my office hours have been really busy the last couple of days. So if you need an extra day to get your absolute best in, let me know, especially if you haven't asked for an extension yet this quarter, that'll be okay. Especially knowing that the grader is still grading homework 3. I don't know if he'll be able to get right to homework 4 right away. I do apologize on his behalf for, I like to have a week turnaround, and now it's been a bit since you submitted homework 3. So you should be having that feedback.
I'll help him if I get to grade my own.
In all fairness, I think homework estimated was like 26 pages.
Yeah, these are big assignments.
Times
There's a
that
lot
by, like,
going on here.
Times that by at least 20, and I understand what's taking so long.
Yeah. I do though appreciate all of the work that people have been putting into those assignments. I know they're long, I know they're tedious, but I really have been seeing the learning when I talk to people about how to solve these problems. I see that learning, and that will show on the exam. The reason that I can give the difficulty of the exams that I do, and they still end up having reasonable grades at the end of them, is because of the work that you all put into the assignments. And I would not be able to have a class environment that has this much learning if we didn't have this agreement that I torture you a little bit and you rise to the challenge. But I'm hoping that people feel like it's all worth it. If you feel like it's not all worth it, let me know. I'd be happy to have a conversation with you about how to try to improve the class for your experience. That is something that is very important to the eventual landing point for a course as you figure out how to teach it, is the actual student experience in that course. Since I'm not taking the course, I get a sense of what that's like, but I'd like to hear it directly from the source. How are you doing? What would you like to see as improvements? I can't guarantee that I make them, especially in the middle of a quarter, but that is very useful for the next time I teach the course.
I'm afraid to have you bias. Like,
Yeah. So last time we talked about the concept of a universal language, this Turing machine that could represent every Turing machine string pair. And then we wanted to figure out what language class that language was. And we showed that that language is recursively enumerable, meaning that we could spit out all Turing machine string pairs where that string is accepted by that Turing machine. That means that we could spit out every program and every input to a program that creates a meaningful output or terminates the program with an output. We could actually come up with a process that would eventually, no matter what algorithm you give to me, whether it's Dijkstra's, whether it's, I don't know, Bellman-Ford, whether it's some other algorithm, this process would eventually output it, which is wild to think about. But then also for every possible input. So eventually, this algorithm would output Dijkstra's on the exact graph that is the current cities and distance between them within the United States. At any level of finality or fine grain that you want to think, just cities larger than 1 million, cities larger than 1. Eventually, this process would output Dijkstra's algorithm applied to every single city in the United States exactly as it is. It would take an extremely long time, again, probably longer than the universe has left. But this process would eventually do that. So that's cool. That was part 1 of this proof of what language class this is in, but to show that it's not more specific than this, we need to show that the universal language is not recursive. So that's the next step of what we want to show. We'll proceed with a proof by contradiction, because that's how we roll in this class. We're going to start by saying, all right, let's assume that it is recursive. This means that since it's recursive and we know a recursive language's complement is also recursive, that means there's a Turing machine that accepts the complement of the universal language. So we just invert acceptance and rejection. If we invert acceptance and rejection, we can transform this machine into a machine that accepts the diagonalization language. And we're going to define this here on the next slide. But we can show that the diagonalization language is not recursive. Much more easily than we can show that the universal language is not recursive. So if we do this, we can do that. Here's how we're going to do it. This machine transforms its input into the pair WW. That's the input string and the input string. We're then going to have this new machine simulate what the original machine that does the complement of LU. So we're going to use the machine that simulates the diagonalization language on the machine that simulates the universal language for this pair WW. So yes, W, where the first one is the Turing machine that accepts that, and the other is a binary encoding of point. So since now we have this acceptance, we now know that M accepts the complement of the universal language. We know that M will accept WW if and only if this machine M sub I does not accept W sub I. But that creates a contradiction. This machine M prime accepts W if and only if that string is in the diagonalization language. So we need a Turing machine that accepts and recognizes the diagonalization language. Since that's not possible, we can conclude that the universal language is not recursive. So let's go show that the diagonalization language is not just not recursive, it's not recursively enumerable, which is what we decided when we showed something like this is the equivalent of the power set diagonalization. We know that that's not recursively enumerable, so let's actually go show that. The diagonalization language says we're going to have strings, enumeration of all binary strings. We're going to have Turing machines that are enumerations of all possible Turing machines. Then we let the diagonalization language be all strings, the ith substring, the ith string W, some binary string, such that it's not accepted by machine I. So the diagonalization language is all strings such that they're not accepted by the associated machine. So we're going to pair up the infinite natural numbers of binary strings, map them to that. Map all Turing machines similarly. The diagonalization language is just all machines that don't accept that equivalent binary string. Does that make sense? Or does that? Let's say we have binary strings. All of those binary strings are 0, 1, 0, 0, 0, 1, and we would have a natural number counting this 1, 2, 3, 4, etc. To where this represents the binary representation of this number minus 1. Then we would come up with, all right, we know Turing machines can be represented in binary. So we're going to just continue this process until we find some binary string that represents some Turing machine. Once we have some Turing machine, we're going to put that here. We're just going to call this TM1. And this is going to be TM2. And as we iterate and find the first legal Turing machine, the next legal Turing machine, the next legal Turing machine, this is going to continue forever, this is going to continue forever. So the diagonalization language is all string Turing machine pairs, where if we ran this input on this Turing machine, it would reject. This says if this Turing machine does not accept this input, then it's in the diagonalization language. So this is kind of like accept. And then is it in the diagonalization language? So this is just the opposite of this. Whenever there is maybe this Turing machine accepts 1, then it's not in the diagonalization language. So now we just want to define the set of all Turing machine input pairs such that it doesn't accept that and it's in the diagonalization language. So every machine that is in here. So we're going to assert that this language is not recursively enumerable. And how do we go show that? We can say, suppose that the diagonalization language is the language of some machine, right? Because there has to be an existing Turing machine that recognizes the diagonalization language, or can at least accept all strings that represent Turing machines that are in the diagonalization language. So this immediately produces a contradiction. What is that machine going to do on input string W sub I? If it accepts W sub I, then by definition, that can't be in the diagonalization language, right? Because if that machine accepted that string, then by definition, according to this machine accepts this string. So what happens when we do this on the machine that recognizes the diagonalization language? If this is every Turing machine that can possibly exist, if a Turing machine accepts the diagonalization language, one of these machines is going to be that machine. What happens when this reads that string? So if it accepts it, by definition, it's not in the diagonalization language, by the definition of the diagonalization language. And if it does not accept it, then by definition, it is in the diagonalization language. This is a problem. Wi is in the diagonalization language, and it's not in the diagonalization language. This means that no Turing machine can exist that can define this problem. We found that contradiction by defining the Turing machine that accepts this string. If it accepts it, it can't be in the diagonalization language, which means that this machine doesn't accept the diagonalization language. If it isn't in the diagonalization language, then it accepts it as part of the diagonalization language, which by definition, it can't be in the diagonalization language. So that's our contradiction. Does that make sense to people? So it's both in it and not in it at the same time, which can't happen.
Sort of like the paradox of, the set of all empty sets.
Yes.
It can't have itself in it because then it's not the set of all empty sets.
Yeah.
Then it can't be complete.
Right.
The set of no sets.
Yeah. So that's just kind of it's a fun way of proving that, but it works. We can show that because of this, there is no Turing machine that can define the diagonalization language. This isn't even recursive. This is saying it's not recursively enumerable because it can't accept this string that is part of it. So we can show that the diagonalization language is not recursively enumerable. So we backtrack to the prior slide with this proof. And now can state that since we know the diagonalization language is not recursively enumerable, then we set up, if the universal language is recursive, we can set it up such that eventually it spits out a Turing machine that recognizes the diagonalization language. We know that's not possible, so this process also can't be possible. How are we doing on that? Any questions, clarifications, confusions? Yeah,
Isn't this also how they'll prove the theorem that if we not prove that the Turing machine will halt on an infinite loop?
it's similar.
Because we have to make a Turing machine to then prove, then verify that one, but then you have another one to verify the verification, but they can't verify each other.
Right. Yeah, it's a little bit more, the halting problem is a little bit more complicated, but we'll get into that. Either today or tomorrow. Yeah, the idea is a proof exists. We can show that if we could do this, then we could do something that we can show is impossible. And that's the form of a lot of theoretical computer science proofs. We can't directly show something, but we can show that if we could do this, then we could do something else. So we can show that that something else is impossible. So we create threads between similar problems that say, if we can prove one thing, then that proves something else, which proves something else, which proves something else. Or if we can prove something else is impossible, that proves that something else is impossible and something else is impossible. All right, we thought we were done with grammars. We are not. We thought we had the most powerful version of grammars. We have not seen the most powerful version of grammars. So I think I said at some point that context-free grammars have no restrictions on their productions. This is not quite true. Anyone have any idea of what restrictions exist in context-free grammars? What could we relax as a constraint in a context-free grammar to make them even more powerful?
You have multiple non-terminals on the left.
The single non-terminal on the left?
Yeah, you have more than one non-terminal on the
Yes.
left.
In fact, not only non-terminals, you can also include terminals. So that's exactly right. The right-hand side has, as Palpatine would say, unlimited power. And on the left, we have a single non-terminal. And that's all we can, it's a definition, right? If you're thinking about how objects are defined, the left-hand side is just, or maybe even a variable declaration. You have a single variable. But imagine now if you could define what would happen if you could see multiple variables in a row or multiple statements of a certain kind in a row. What does that mean when we pair some concept together? So multiple terminals or non-terminals on the left-hand side of a production. This gets gross. So multiple terminals on the left-hand side. I think one of those is supposed to say non-terminal, yeah, multiple non-terminals on the left-hand side, or one or more terminals on the left-hand side. So there's a typo there. We're going to relax all of these constraints. Any number of terminals or non-terminals can be used on either the left-hand side or the right-hand side of a production. However, there must be at least one terminal or non-terminal on the left-hand side. You can't say lambda arrow something. That is not allowed, because that has no meaning. We can turn nothing into something. We have to define it in terms of something real. But other than that, we place no restrictions on what or how many of that. So lambda is not allowed at all on the left-hand side of a production. The real question that I have for people is, what language class does this map to? In the way that when we had a context-free grammar, it mapped to context-free languages, we've now discussed the language class that this type of grammar represents. What do we think it is? So it's either recursive, recursively enumerable, or not recursively enumerable. One of those three is the answer. Thinking about just the structure of this grammar, what becomes your guess?
I have to say, you know, definitely not enumerable. No, and therefore, because diagonals can't be recursively enumerable, not recursively enumerable.
Good guess, but it is wrong. So it's either recursive or recursively enumerable. Any guesses between those two? What makes you say recursive?
Is it, I don't know, I just guess.
That's a good guess though, because it's right. So it maps to, so of course it's more powerful than context-free grammars. Recursive languages, actually I was wrong, it is more powerful. It is actually recursively enumerable. Oops. It is recursively enumerable, my bad. So this means that I was attaching myself to this very last idea of Turing machines and unrestricted grammars have the same power, but that's because Turing machines can go into infinite loops. This type of recursion can also go into an infinite loop, and because of this, it is recursively enumerable. So let's talk about unrestricted grammars in more detail and see how gross it is to try to solve problems with them. I will not have you do any of this on an exam. In fact, I don't even think I have you doing any of this on homework. It's just not fun. It's not fun, and it's not particularly useful to be able to make a grammar for a recursively enumerable language. If you were going to do that, you might as well construct a Turing machine for it. Or you might as well write a program for it. A program that might go into an infinite loop. So it's not an algorithm, because it won't always give you an answer, but you could still write a program for it. So what is the recursively enumerable procedure for this? How do we go about figuring out what is every string that is in the language? This means that it may be that you give it a string that's not in the language and the grammar never terminates. It never terminates and rejects. It just spins forever, going from production 1 to production 2 to production 3, back to production 1, 2, 3, 1, 2, 3, 1, 2, 3, forever. Maybe expanding into more and more and more non-terminals in a way that never ends. So as always, we start with a single start non-terminal. That is the starting position. We have to have some production that is S arrow something. It's like the beginning of a program. You can't write a program that doesn't have a line 1. You need a starting place. There is an instruction, even if that instruction is immediately enter an infinite loop. We would then find all strings. If we could apply a single production, S arrow this or that or something else, we look at what can we get? What are all of the legal strings in the language that we can get with a single step from that start non-terminal? We have a finite number of productions. There's a finite number of productions. The list will also be finite for this. Then we can find all strings derived within 2 steps, within 3 steps, within 4 steps. This becomes exponential complexity, or it is exponential complexity. But we would still be generating new strings in the language if we could find a way for this grammar to terminate. You just continue this process for every finite number of productions. And we know that any string that's in the language will terminate in some finite number of productions. It's only those that aren't in the language that might spin forever. But we don't care if it's recursively enumerable about being able to say no. We just need to say yes for every string that is in that language. So this process won't terminate, just like everything else we've talked about that's recursively enumerable, but it will continue to produce more and more and more new strings in that language forever, assuming this is an infinite language. If we took this process, we could design a Turing machine for it to do exactly this. And since we can design a Turing machine to do it, then it is recursively enumerable. If we wanted to say, let's design a Turing machine that mapped to this concept of an unrestricted grammar, that is a lot harder. If we have a Turing machine, we want to derive an unrestricted grammar that accepts that same language that the Turing machine does. Don't try it. It's a very long proof. The book goes through it if you're curious. I'm not going to go through it here. It would take a class period or 2 by itself. And it's just not worth our time. But do note that it is possible to do. It's just absolutely disgusting. There is one interesting restriction to unrestricted grammars called context-sensitive grammars. And context-sensitive grammars are the one that map to recursive languages. But we're gonna make a single restriction to an unrestricted grammar. And now we're going to be able to conclude yes or no in a finite number of steps. So there are lots of classes of grammars. You can do different things of relaxing constraints or adding constraints to different versions of grammars between context-free grammars and unrestricted grammars. And most of these language classes don't really tell us anything. They don't produce a class of languages that is interesting enough or relevant enough for anything that we study to be interesting. However, context-sensitive grammars is the one that is. So most of them are not interesting. And one class that is heavily studied is, sorry, it doesn't produce recursive, it produces linear bounded automata. So the equivalent class of linear bounded automata. It says that if there's instead of a tape that goes, it's infinite, there's that left bound and a right bound, and we only allow the tape to be as long as the input is. So context-sensitive grammars allow us to produce this class of languages. So as before, we can have one or more terminals and non-terminals on both the left-hand side and the right-hand side. However, the big restriction is that the number of total symbols on the left-hand side must be less than or equal to the number of symbols on the right-hand side. So why is this interesting? Every time we apply a production, the length of that production is only ever increasing or staying the same. We can now define a normal form with productions in a particular form where we have something like this. We're going to call it x capital A y arrow x b y, where the idea is that A is converted into Y if there is the associated context that A appears after X and before Y, therefore B can appear after X and before Y. That's where we get that concept of context. So it's context sensitive. I'll give you an example of just even how bad context sensitive grammars can get. So one restriction, this idea can't generate the empty string. Because it can only ever increase in size, we get S arrow something. So we can't make that go away and produce nothing. So no context sensitive grammar can produce the empty string. So we just allow it in the definition of a context sensitive language. So let's get an example. What would it look like to try to relate a language that we showed via the context-free pumping lemma that this language was not context-free? Can we produce this with a grammar? It's a really simple language. Something like A to the n, B to the n in context-free was a very simple grammar. That was just AX, B, or lambda. In this case, though, here is the context-sensitive grammar for this. Take a few minutes and stare at this and try to figure out how or why this produces A to the n, B to the n, C to the n. And then we'll draw it out. So think about the sequence of productions that have to go through to be able to produce ABC, which we know is in the language. We need to be able to produce A, B, B, C, C. That's in the language. A, B, 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 C, C, C. That's in the language. What are the sequence of productions we have to go through to produce those?
Have this agency, we're gonna pay a BC with a capital increase in the middle. With the, AB, so it can go BA, then how do we get AC? Because we have to have A adjacent to a C, so we can't get to capital B at all through this production. So we have a bunch of debt production below it. This capital A cannot be adjacent to C by the definition of a star.
Let's see that that's not true.
A to B pushes the A to the other side of the B, the second production.
Yes. So these are the kinds of productions that we have not seen in any other kind of class of language that allows us to do things like invert or change where things are with respect to each other.
But that was just generating a B next to it, and then you could do.
No, that would be the case if there was not, you have to have multiple symbols on the left. So you have to have this particular string somewhere in your derivation, and you replace this string with that string, which does the equivalent of flip where the A and the B are. It's really annoyingly complicated.
Just starting,
Do you see and A and B though? Terrible. Terrible, terrible. So we can derive this one pretty easily. This is just S arrow ABC. Really easy to do. How do we get the AABBCC? How do we even start that? It's not directly ABC. There's only one production that we can apply. So let's see if we can get there. S arrow, we want lowercase a, capital A, lowercase b, capital C. What can we do to this?
have to go do AB to then swap B to A, so we
Yeah.
have to move it to swap.
We have that substring, which represents this left-hand side. So we can now swap the order of A, B, capital A, C. Hey, we got the A over to the side of the C, where we have this AC now.
Then you're gonna replace that AC with a B, E, C, C.
Yep. So this A, we have A, B, but the AC is now completely replaced with B, B, C, C, and for some reason I thought I'd left myself enough space. Even I was wrong.
Let's just draw another arrow.
I wanted to eventually generate this one, but that's gonna be gross down here somewhere. But yeah, so now what do? We have the two B's and the two C's, we need to produce another A.
You're gonna flip the
We'll
B,
flip.
B.
Yep, the B going to moving the uppercase B to be first. So we have A, and now taking the BB, we're flipping that to where the B comes first, then B, B, C, C. And now you can replace the AB with the AA that terminates. So we have AA replacing this AB, BB, CC, which is that.
Oh, so it doesn't add two A's, it just.
Yeah, replaces the A capital B with two A's. Yeah, the left-hand side gets replaced by the right-hand side. It's no longer non-terminal gets replaced with something. It is the entirety of the left-hand side that gets replaced with the entirety of the right-hand side. Yeah,
It's kind of like a recursive macro expansion.
yeah, that's actually a really good way to think of it. So we can see that this A is going to move all the way to the right-hand side to where it becomes a B, which is going to move all the way to the left-hand side where it becomes more A's. And we can recurse this by now changing that B back to an A. And that's what creates the additional A's, sorry, the B's and C's terminating with the final A that gets produced. So this non-terminal is just ping-ponging back and forth between the start and the end, the end of the A's and the start of the C's, producing the B's and C's, the A's, the B's and C's, the A's, the B's and C's, the A's, until it's done. And it terminates with each one of these.
There's gotta be a way to implement this without doing all that.
There's not, this is as simple as it gets, as far as I'm
You
aware.
couldn't implement this with like a Turing machine that had a rewrite, they could read two characters and write, or like read or write.
Because
an
well,
arbitrary
you
number
said
of
if you're
characters.
making context sensitive, you might as well just make a Turing.
Yeah, the issue is it's a linear bounded Turing machine. So what's the input on this would be the string that we want to verify is in this language or not. So we wouldn't have any more space than this to be able to do that. How could you verify that it's in the language? We would need some way of, on a second tape, storing the number of A's that you see, mapping exactly that many B's, mapping exactly that many C's.
I mean, that just sounds like a simple program like that.
Yeah, it wouldn't be too bad in a linear bounded automata, especially if you could do a linear bounded automata with 2 tapes.
I mean, even from like, just the basic, like CS focus, what do we do, that's basically what we have variables that track.
Yeah.
The number of. Yeah.
This is why we write programs more like Turing machines and states than we do like these grammars. The reason you haven't seen something like this before in any CS class is because it is worse to think about, but it maps to that same class of languages, which is really interesting to think that there's another way to think about it. It's just not a way that we want to interface with when we are thinking about how to write programs.
But this is how you would write it. Kind of, if you were writing it directly onto the machine and you wanted to preserve or have like the least number of moves between memory locations.
Yeah, so if you wanted to design a Turing machine that iterated all of these, produced ABC, and then AABBCC, and then AAABBBCCC. That's more like what this grammar would be. It's not a verification of a particular string is in this or not, but it would be this generates all possible strings that adhere to that language. Now that Turing machine is a lot more complicated because now you do have to ping pong back and forth, adding some B's and C's, adding an A, adding some B's and C's, adding an A in order to generate the next string in sequence. So it does map to exactly what you would write a Turing machine for if you were writing that program, because that's what this grammar does. It's both a verifier, what are the sequence of productions, and it's an iterator to be a generator to be able to produce every string in that language. Which is cool. Rather than write out the AAABBBCCC, it's on the slide. We needed a single production to produce ABC. We needed what, 6 to produce AABBCC, and here we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, so 12 total with 11 transitions. Yeah, it gets worse. So yeah, that's the derivation for AABBBCCC. More about them, we can show that all of these are also recursive. However, the classes aren't the same. There are recursive problems that are not context sensitive, which also tells us that the class of linear bounded automata is also less powerful than a simple Turing machine. That becomes your proof for why this is the case. Everything that we've talked about so far can be easily summarized in a couple of nice Venn diagrams called the Chomsky hierarchy. So the first image shows us everything, every language class that's inside of each other, that are subsets of each other. So we first talked about regular languages. Then we talked about context-free languages, but we found that the non-deterministic context-free language was a different class from the deterministic context-free language. So deterministic context-free is a subset of context-free, and regular is a subset of that. They're all within each other. Outside of context-free, we have context-sensitive, which map to that linear bounded automata that we just talked about. Outside of that are recursive languages, everything that a Turing machine could both accept and reject. Outside of that is recursively enumerable, everything that a Turing machine could either accept or reject, but not both. And then not recursively enumerable is outside of the Chomsky hierarchy, something that, like all reals between 0 and 1, we don't have a process that will be complete. We could give an example. If someone said, here is a process that generates an infinite number of real numbers between 0 and 1, we could give a counter saying, your process will never generate this number for any process that could be given to us. There's one other piece to this that is a kind of zoomed in piece of this. That is, we're gonna zoom in on just the context free. So this subset right here, zooming in on everything that's inside of that. And that gives us this one, where we can now say deterministic, context free, and linear are regulars inside of both. All regular languages are both deterministic, context free, and linear. But there's some overlap between deterministic, context free, and linear. Some languages that are deterministic, context free, not linear. Some that are linear and not deterministic, context free. But all of them are context free. So this is every language class we have even hinted at so far and how they relate to each other visually, just in terms of the associated power of those languages. Language classes, I should say. So that's kind of a bird's eye view on everything that we've talked about in terms of how complicated are they, what kinds of languages can they accept, how do they relate to each other. This is computer science from the bird's eye view, as these different language classes and the power of these different language classes and what we can do with them. How are we doing? That's kind of a lot to take in. But what's cool from here is we've now talked about all of the theory that we need to talk about compilers. We finally did it. In a class called compilers, it took us 6 weeks to get through just the prerequisite content to be able to talk about compilers at this pace.
Just a meme image of the skeleton that falls over.
Yes. Yeah. So this is really cool, but now an understanding of all of this will allow us to be able to state, what does it mean now to construct a translation algorithm from a programming language down into machine executable code, or some middle step to that, be that bytecode, be that assembly, some form of middle step. But we can now describe how to translate logic into other logic in different forms. So we're gonna give you, or at least start to give you, an overview into what that looks like. But before we dive into that, there's one more thing to cover that's not particularly related to it, but it's still really interesting. I know, we really want to dive into compilers, but we are going to talk about things like the halting problem and what are the real limits of algorithmic computation. This is everything that you need to know to be able to write one, but there is some theory outside of what is possible and what is not. But we also have the prerequisite content for that now, being able to talk about Turing machines. So we've now discussed at length what Turing machines are capable of, but we want to be able to discuss what Turing machines can't do. And yes, that's anything outside of recursively enumerable languages, but what real problems are there outside of that that are not just list all real numbers between 0 and 1? List all sets in the power set of binary numbers. Those are interesting, but not really particularly useful applications. So let's talk about what actual theoretical results we can get from analyzing what Turing machines are capable of and not capable of. To do this first, we need to define two terms, computability and decidability, and they're going to map to recursive and recursively enumerable languages. So something that is computable is the equivalent of recursive. So a Turing machine that computes the value of a function for everything in its domain. If this is true, then that function is computable. If something is uncomputable, then no Turing machine exists that could find the value of that function for all values of its domain. Decidable, now instead of just being able to compute, now we're deciding. We're saying yes and no to a set of problems. If a Turing machine that exists that can answer yes and no for every instance of the problem in the domain, then it is decidable. If a problem is undecidable, then no Turing machine exists that can answer yes or no to that question. So computable is just mapping inputs to outputs. Decidable is mapping inputs to yes and no. Restricting the output domain to just yes and no. So it's really more like automata that we've discussed and transducers. What's fun is depending on the domain, you can have different results of decidability. So we apply this algorithm to one domain, it's decidable. We apply this algorithm to another domain and it's not decidable. Which is very interesting. I will, since we have a couple minutes, I will very briefly introduce the concept of the halting problem, and we'll dive into this in a lot more detail. And on Monday, we will have movie day where we get to watch Veritasium walk us through the issues with math. The one time that I will show a video in any class that I teach, but it's worth it. It's a cool video. So we want to define the halting problem as determining whether a given Turing machine is going to halt on a particular input. So we want to design a machine that takes as input another machine and a string, and output whether that machine halts on that input or whether it enters an infinite loop. So we need a single machine to do this for an arbitrary machine and an arbitrary string. You can imagine asking or writing a program that determines whether your program in a particular programming language has an infinite loop. You might look for something like while true, and if you could parse and find somewhere that says while true, and then in none of those other lines of that code, there's no break statement. There's no system.exit 0 in Java. There's nothing that terminates the program from within that loop. Then you might be able to say that it goes into an infinite loop. But is that the only kind of infinite loop that you could have? What about just a while with a statement that never approaches the termination condition? How would you be able to state that arbitrarily? You could write a program for a particular function, but for an arbitrary program, so this is impossible. No program exists that can do this. So the way we're going to do it is going to be defined on Monday. Since this is there's no way I'm going to be able to do this in anywhere close to a minute. So we will introduce it. We'll watch a visual video on it. And hopefully it will make more sense at that point. But tomorrow review, Friday exam, we'll come back and continue this train of thought on Monday. Not taking too long, and we'll finally talk about filers. All right, I have office hours starting now for the next hour before I go torture my game dev students some more. I can answer any questions you have.
Yeah, it's about right now.
Yeah.
Sitting here.